Hello and welcome to continuous functions. So the idea here is we've been looking at limits, right? So we've been looking at what happens as you come from the left, what happens as you come from the right. But now we want to see if we can simply just pass straight through a point smoothly. So the basic idea is we want to know essentially if a function is in broken pieces or if it is connected. So it's not the official definition, but we consider a function to be continuous somewhere if essentially we can draw it without picking up a pencil, right? So can we draw a function without picking up our pencil? So a couple definitions where we can get sort of exactly what we're referring to with a continuous function. So function f is said to be continuous at the point x equals c. So continuous at the point x equals c if the following is true. So if the limit exists, meaning if the left and right side limits are equal. So if the limit as x approaches c of f of x exists, right? So again, namely the limit as x approaches c from the left is equal to the limit as x approaches c from the right. And then beyond that, and not only does it exist, but that limit as x approaches c is precisely the value at x equals c. So the limit as x approaches c of f of x equals f of c. So we've seen functions, named specifically ones where we had a hole, where the limit existed, but the function value was something else. And so if we were to draw that, we would have to stop at the hole and then start back up again after the hole. So to have a continuous function, we need to be able to pass straight through the point. Let me give myself a little more room. And then the other definition we have is a function f is continuous on the open interval I if, so here continuous on the open interval I, if the function is continuous every point x equals c for every c in the interval I. So we will deal more with intervals on which a function is continuous in future videos. For now, we are going to focus on specifically at a point. So for example, let's consider the function of f graphed here. So on this function, we have a straight line running from the point -5, -2 to the point -1, +2. We have a closed circle at that point, -1, +2. Then we have a straight line from that point down to the point 2, -1. There's an open circle there, open circle at 2, -2. And then we run from there straight up to the point 5, 1. But there is an open circle on that line at 3, -1. And then we have our closed points at 2, 0 and 3, 1. Right? So we have to determine if f is continuous at the following x values. First up, we have x equals -4. So if we look at x equals -4 on the graph, we are looking at this location here. That line definitely seems to just go straight through at -4, but we could always check. So if we look for the limit as x approaches -4, coming from the left, we appear to be approaching -1 for our y value. And then if we do the same thing coming from the right, once again, we appear to be approaching -1 for our y value. And then the last thing we want to check is simply what is f of -4? And in this case, that is also -1. So these are all equal. So that means that it is continuous at x equals -4. So now let's do the same thing for x equals -1. So at x equals -1, here we look at what's going on. Coming from the left, we are approaching a y value of 2. Coming from the right, we are also approaching a y value of 2. And the function value is precisely 2. So once again, we have the limit as x approaches -1 from the left of f of x is 2. The limit as x approaches -1 from the right of f of x is equal to 2. And f of -1 itself was also equal to 2. So once again, these are all equal. And so we are continuous at x equals -1. Next up, we are supposed to look at x equals 2. So at x equals 2, let's see what is happening. Coming from the left, y is approaching -1. Coming from the right, y is approaching -2. And at the point itself, we're at 0. So we actually are hitting 3 different values. So once again, the limit as x approaches 2 from the left of f of x was -1. The limit as x approaches -2 from the right of f of x was equal to -2. And the limit as x, or sorry, not the limit, the value at -2 was equal to 0. So these are not all equal. So it's not continuous. At x equals 2. Sorry, that should be function value at f of +2. So in this case, the limit did not exist, right? So the reasoning for why the limit does not exist. With the limit not existing, it's impossible for the function value to equal the limit. Then at x equals 3, so here is our 3. And as we approach from the left, it looks like we are going to -1. As we approach from the right, we are going to -1. But then our function value is 1. So if we look at 3, the limit as x approaches 3 from the left of f of x is -1. The limit as x approaches 3 from the right of f of x was also -1, if I remember correctly. And then the function value is 1. So f of 3 is 1. So these are not all equal. The limit does exist, but the function value does not equal the limit. So this is not continuous. At x equals 3. And again, the f of 3 is not equal to the limit as x approaches 3 f of x. So those are sort of our main ways that the function may not be continuous. The other possibility is if the function is not defined at that point. So instead of having a hole and then having a point up above, if we simply had no point at x equals 3, then we would also say that the function is not continuous, because it's impossible for the limit to equal the function value if the function itself is not defined. So that is the basics for determining if a function is continuous at a point.